now. All right, it is 9 o'clock. I am getting started. So I actually have to make an agenda today because the lab actually does require a lot of concepts. Um, this is basically just the overall agenda of what I need to go through today. We have to go through a few instructions. JMPI is one of those. We are going to go through one of the conditional branch instructions, maybe JCI, maybe JSI, we can decide later on. And then we also have an increment instruction that is kind of helpful, in the lab for today. And I also need to show you guys how to log the execution of a program as a whole. So the process of doing that is important. It is in the lab anyway, okay, but I'm going to demonstrate how to do it on the screen. So, that might actually be helpful. And just as a side note here, maybe taking notes can be important. Um, if you cannot like write down everything that I do on the screen, that's okay. Just jot down the time because the video will be available within about 10 minutes or so after the lecture ends, which is just about when the lab starts. All right. I am grading the exam, okay? It's just that it's hard for me to find a solid block of time to do it, and I really want to do it in a single block of time, so that everything stays consistent. If I break it up into multiple sessions, I sometimes find that I may not be as consistent as I would like to be. All right. So what we'll do is we're gonna start with the JMPI instruction. And the way I usually start is the opcode table, which is also something that you might want to consider is to download the opcode table, so that you have a copy on your own, and then you can use your own copy for annotations and adding your own descriptions of the instructions. So the JMPI instruction is this one on row 9, and we'll go through the columns one by one. Column A is just the opcode, which is the 8-bit pattern, so that you store this bit pattern in RAM, and then when the processor decodes that byte, it will know what to do with it. The mnemonic is JMPI, which stands for jump immediate. Okay, so the I here is immediate, and it will take, guess what? Not surprisingly, an immediate operand. And an immediate operand, as we talked about last time with the LDI instruction, is nothing more than just a constant that is resolvable at assemble time. So by the time the program is assembled into the bytes, in the RAM file tab, those constants or the values of that expression needs to be resolvable. So what is interesting, what is mysterious, is the RTL. Okay, so the RTL tells us that the operation of the program counter the program counter is getting updated by whatever it is pointing to. Okay, so that essentially is what this expression is about. This is using C syntax, so the asterisk has exactly the same meaning as in C or C++. So what we'll do next is we're going to hand assemble a program, okay, just so that we can see how it works. So we'll go ahead and start up Logic Sim. I think I might have closed the one from yesterday, so I'm going to start it again. No big deal. All right. And then we'll go ahead and load the processor. There we go. All right. Um, and because the opcode of JMPI is 40, okay, we know that because over here we can see that it is 0100, which is a 4, and then 0000 is just 0 in hexadecimal. So we know the opcode is just 40, but we also want to include an immediate operand, which is where we want the jump instruction to branch to. So that's exactly what we're going to do. So we switch back to Logisim, and then we put a 40 here. It is the first instruction. And jumping back to location 00 is not very visible, so we're not going to do that. Instead, I'm going to jump to location FF. Okay, so this is the program that we have so far, and we can actually run the code. Okay, we can just run the code, as it is. Okay, so that will give you an idea of what it looks like. I do have to change the tick frequency to something that's lower. Maybe 64 hertz would do, and then we'll go ahead and enable ticks, which is also Control K. So what you will see, oh, that's still too fast. That's okay. We can lower it some more to, let's say, 16. I think that's a lot better. You can see how it is really in a loop. It is going between location 00 to location 255 or FF and then back to location 00. Okay, so we'll go ahead and take a look, we'll take a closer look at this program and see what it is, why it's doing this. So Control K to stop the clock again. Turn the clock to the low state, and then click this reset button. So this way, I'm not changing the program at all. Not that this is a difficult program to re-enter. All right. So what we'll do is we're going to go through the decode. Well, not decode, fetch first. So Control T is a fetch. So we now have the opcode in the 40 opcode is in the instruction register. Control T again, that increments the microcode pointer. Control T again, it increments the program counter. This is actually significant because now the program counter is actually pointing to FF already. It is no longer pointing to 40, which is the opcode. The opcode is already fetched in the instruction register. And then the next Control T is going to decode. So right here we have decode, which means the microcode pointer is now at 400. You can also see the ROM is addressing location 400 with the content of in hexadecimal 1F80006. Okay, so that means we are now at the quote unquote execute phase of an instruction execution cycle. This is the last phase of executing an instruction, which also means the rising edge here with the clock is going to change one of the registers or a few registers sometimes, so that the program is going to do whatever the opcode is asking it to do. This is also called the implementation of an instruction, okay? Because the fetch cycle is not an implementation. That's just getting the content or getting the opcode into the microcode pointer, and then to decode it. So fetch and decode is what it takes to get to the execute phase of executing an instruction. So we are now just about to execute the instruction. So once again, by this time, you probably should have a piece of paper with the processor architecture on it and color coding the components that are quote unquote active. In other words, what components do we examine first in order to determine what this program or what this instruction is doing? I'm not going to repeat those few components anymore because we have talked about that multiple times already in the past. So I'm just going to go straight to the two components that are active in this case. One is the program counter because we can see PCEN is bright green. We know that the program counter is about to update. We can also see the RAM is also selected because RAM select is a 1, which means the RAM component is active. It is going to do something. So at this point, you can you can tell me which one do you want me to start first, okay? Because as it turns out, it doesn't really matter which one I start. We can still come back to the same story of what this instruction is going to do. So you guys get to pick the program counter or RAM. RAM, okay, sounds like most people want to do the RAM. Okay, so we'll start with the RAM. So with the RAM, I am assuming that you already know what the RAM does and what each port of the RAM is going to do, because that is a part of what you are expected to study. It is also a part of what the lab is designed to help you, understand. So we're going to start with the RAM. The RAM is being selected, which means it is active. It is going to do something. So the next question is, what is it going to do? LD being a 1 means we are reading from RAM, which also means the D port is going to have the content of the location that is currently addressed. So now we now have two additional questions, which is, and you guys can choose which way you want to proceed. We have to either look into the D port and see who is using the data, or we can look into the A port and see who is specifying the address. So which one do you want to use? Which one do you want to go first? The D port? Okay, we'll go with the D port. So we know the D port is the output at this point because we are reading from RAM. So we look at this node and then we go like, okay, who possibly can be paying attention at this point? So we go to all the endpoints. This is just an output pin. It's not really that significant. It's only for logging purposes. This is the instruction register. It is not enabled. So that means the instruction register is ignoring the input. So that's not important. This is the output of a demultiplexer. And then the demultiplexer is turned off at this point. So that means this connection is not of use to me anymore. This is an input that eventually may go into the register bank, but we can also see the register bank is disabled. Nothing in the register bank is going to update because the input enable is a dark green. So we are left with only one possible thing, which is this one here. So we can see that this is input one. The select is also a one. So the output is using input one. So now we track down the output, which goes into another multiplexer. So with this other multiplexer, let me point somewhere else first. So with this multiplexer, the select is a one. This is indeed input one. So now we know this input one is going into the program counter's D port. The D port of the program counter is what you use to update the content of the register, and the program counter is enabled at this point. So that means whatever the D port of RAM is outputting is going to the program counter so that the program counter will be updated using, in this case, the content of FF. Now, in LogicSim, you can easily verify that because if you click on the node, it will tell you what it has. All right, so that addresses the question of who is making use of the content that is being addressed, but it does not answer the question of who is specifying the address to the RAM. So now we track down the A port. The A port is coming from the multiplexer here. This particular multiplexer has a select of 1, which means input 1 connects to the output. So we track down input 1, and not really surprisingly, it comes from the program counter. So that means we are using the program counter to specify the address. Whatever is at that location, the content of that location is in return going back to the program counter to update itself. Are we good so far? All right. So that is hardly surprising, I hope, because that's exactly what the RTL is telling you. The RTL is telling you that we are using the program counter as a pointer, go to the location in RAM that the program counter is pointing to, retrieve the content at that location, and then in return use it to update the program counter itself. Are we good so far? All right. So now we switch back to LogicSim, and I'll give it a rising edge, Control T, and your attention should be focused on the program counter itself. So Control T right there, and not really surprisingly, the program counter is now FF. So can someone remind me what is the job of the program counter? What is it used for? And by the way, it's also called the instruction pointer with certain architectures. So what does it do? That is correct. Okay, it tells the processor where to fetch the next opcode. Okay, which means if you change the program counter, you change the flow of the program. It is no longer quote unquote sequential because right now we are already at the next, well, we are almost at the next fetch cycle. Because when you look at the microcode pointer, it is at location 401. We're about to experience a falling edge, which will increment the microcode pointer to 401. But that is going to, okay, so when we look at, let me It's a little bit harder because it always pops the other window on my actual laptop computer monitor. So I have to always to move it back into where you guys can see it. All right, so we are going to go to location 400. Okay, 400 is right here, and then this is location 401. 401 is 2 followed by a bunch of zeros. We talked about this already. What that will do, okay, what that one single bit that is a 1 is going to do is this wire over here, is that node over here. So that will turn into a 1. This is an OR gate, and the output of the OR gate will also become a 1, which means the microcode pointer is going to reset to 000. So we talked about that already. So now we give it a control T to watch the microcode pointer to return to 000, like that. So at this point, okay, we are now going back to the fetch phase of executing an instruction because the microcode pointer is now 000. The clock is low. We are about to have a rising edge. So which location is going to give me the next opcode? Right there. The program counter is FF. This is where we're going to get the next opcode. And this is also why that location is actually highlighted right now. Are we good so far? All right. So now the next question is, what is the opcode? Which instruction has an opcode of 00? Not halt. It's the other relatively useless instruction. Is no op. Okay, no op has an instruction or has an opcode of 00. So that means when we quote unquote execute this instruction, it doesn't do a single thing, right? So we'll go ahead and execute that instruction. By the way, to execute this instruction, the decode will automatically put the processor back to the fetch cycle. But what you need to do is to focus on the program counter. So the next control T is fetch, and that's why the instruction register becomes 00. And then we increment the microcode pointer, which is down here. And then the next one is going to increment the program counter. So when we increment the program counter, which is already FF in hexadecimal, what is going to be the new value of the program counter? What happens when we add 1 to 1111 as an 8-bit number? It gets back to 0. It wraps around to 0. So we're going to observe that. Okay. Control T. Aha. It's back to 00. And now we're going to decode. So the decode is also interesting in this case. I think we have talked about this already. Because what is going to happen is the 00 here will become the 00 over here, and then this extra 0 from the splitter is going to become the least significant 0 over here, which means the decode is going to put the microcode pointer back to 000. And once again, we have a clock being low. So can someone remind me which phase of the execution instruction cycle are we at this point? Sorry? Nope. Fetch. Okay, we're back to fetch. So we are now going back to fetch an instruction or an opcode from location 00 because that's what the program counter is. Have we seen this before? This is how we started the whole thing. All right. So what is new today is really just the fact that, oh, okay, the jump I instruction, the JMPI instruction is new to us. We haven't seen anything like this where the program counter is updated by whatever the program counter itself is pointing at. That is the only thing that is new today up to this point. Okay. I have to point that out because depending on what you're experiencing, you might need to decide what you need to do next. If you're thinking, yes, I get it totally, okay, I follow every single step. In fact, I can already tell what Tech is going to do before he did it, okay? That's good, okay? That means you're getting all the material, you're understanding the mechanism of the processor. Excellent. If you're thinking, well, Tech talks a little bit too fast for my taste, but I think I get it, okay? I can follow that. If I watch the video again, I will get everything. Not a problem. Okay, that's also good, not a problem. Okay, on the other hand, for people who are thinking, I cannot follow anything that tech is talking about, I would consider that a red flag. Okay, so if people are experiencing that, I would encourage you to come talk to me before the class because my office hour is immediately before the class, just so that people can come talk to me a little bit easier. Or after the class, not today because I have a root canal appointment today. Not something I'm looking forward to, but on other days, you can also talk to me after the class, after the lab. Okay, but I do want to make sure that people have an understanding of where they are in the class so that we can take action or make decisions in a different way so that we steer everything back on course. All right, all right. So that is the JMPI instruction, and now we are going to move on to the next item on the list because I keep forgetting what I need to talk about, which is kind of normal for me. Uh, so I think the next item is the add instruction or something that can change the flags register. Okay, excellent. So let's go back and talk about the subtraction instruction because that's also something that we have talked about already. So we go to the opcode table and then we go like, okay, let's go ahead and, oh, let's actually not do the subtraction. Let's do the compare, okay? Because the compare instruction is almost like the subtraction instruction for except for one little difference. Okay, so this is the subtraction instruction. I will highlight both of those and you can tell me what the differences are. Okay, what is the difference between these two RTL descriptions? Yep, exactly. Okay, so in the case of a subtraction, we take the difference and then we store that back into register X or whatever register X is the placeholder for. But in compare, we just perform the subtraction without storing anything back. Okay, so the question is, why are we doing this? This doesn't sound really useful. So in this particular demonstration, I'm going to show you why CMP is actually useful because it will actually determine the status of the flags. So that's what we're going to do. But I have to determine which two registers I am going to compare. So the first part of the left uh, hexadecimal digit is going to be an E because it's 1110. Now I have to determine which two registers I want to compare. Um, let's just pick B and D again, okay? So we want X to be B, which means XX is going to be 0, 1, and we want Y to be D, so that means YY is going to be 1, 1. So that means the whole thing is going to be E, and then the 7, because this is going to be 0, 1, 1, 1. So E7 is going to be the opcode. All right, so we're going to put it into the RAM in here. So we're going to put in what E7, yep, E7. Okay, so that will perform a compare, and then we're going to do a conditional branch. So now the conditional branch is also important, and it is important to know how to read a conditional branch. So the conditional branch instructions that we are focusing on right now would be one of these five. So these five, the only difference between each one of these is which flag we are looking at. Um, for the most part, we should know some of these flags already. We should know what is the L flag, that is from binary comparison. We should know what is the O flag, which is also from binary comparison. We should know what is the sign flag, which is also from binary comparison. The C flag is from binary addition and subtraction because the overall carry and the overall borrow, they're both called the carry flag in this case. And then the Z flag is new to us. Okay, this is the only one that is new to us because we never really talked about how can we check whether two values are the same. We can only tell whether x is less than y, but we can never tell whether x equals to y. So the Z flag is new to us. So which flag do you want to focus on? In other words, we have choices. of, JLI, JOI, JSI, JCI, and JZI. So among these five, which one do you want me to use as an example? Is your pick. Well, I can inject values into the register so they are not the same. So it's up to you guys. I mean, if you want to use JOI because it spells joy, we can do that. Mm-hmm. Yep. We'll start with JOI. Okay, let's get start with JOI. Okay, there we go. So JOI has an opcode of 4 2. So we're gonna kind of put that into the RAM location here. It's going to be a 4 2. And now we have to determine where do we want the program to go if there's an overflow. So I'm just going to put a 04 over here. Okay, so this is going to be the location where the program is going to go. If there's an overflow, I put a 01 here because that's a halt instruction. And I'm also going to put a halt instruction here in case there's no overflow. Okay, so that's the entire program. So I'm writing the entire program without the assembler, but if I want to write the program in the assembler, this is what it is going to look like. So let me switch back to the assembler, and this time we are going to actually write the code. So I like how you guys are following me because I think that's actually helpful, okay? Because if especially if you have your own laptop computer, you can make a copy or take a snapshot of the spreadsheet, once I'm done with the code. So not right now because I'm just about to kind of write the code here. So we have a CMP BD, okay? That's the first instruction. We want to subtract D from B, but without storing the result back into B. And then we have a JOI instruction to location 4, and that's all you need to do, okay? That's one way to do it, but you can also use a label. So let me just illustrate how to use a label. I'm going to use label L1, or better yet, um, we'll say overflow. Okay, overflow is the name of the label. So the moment you press the enter key and wait for the assembler to do its thing, it's going to complain that we do not have a label called overflow, and that's fine because I actually have not defined it yet. And then we put the halt instruction here, and then we define overflow as a label here. A label definition ends with a colon, so that's why this is a label definition. And then after that, we put another halt instruction here. So overflow is actually just the symbolic name of this particular halt instruction. This halt instruction is immediately following the JOI instruction. So do we have any questions about the assembly code here? Hmm. We don't know yet, okay, because it depends on what the values of B and D are. Because I can inject values into registers B and D when I run it in the simulator. So it all depends on what we choose to be the initial values of B and D. Whether the overflow flag is going to be a 1 or not depends on what we choose as the initial values of B and D. Okay, are we good so far? Maybe. All right. So now we want to take a look at the assemble view, okay, just to make sure that my hand assembled program is correct. Okay, so we start with an E7, a 4204, 01, and then a 01. And in fact, I'll just be super lazy and take a screenshot of this. It's a really nifty tool, okay, being able to take a screenshot and then display that like this. Okay, make it always on top. Now we can switch back to Logisim, and then we just compare the content. E7, E7, 42, 42, 04, 04, 01, 01, and then another 01, and another 01 here. So the hand assembled version is consistent with the one that the assembler has assembled. Are we good so far? All right, cool. So I have no use of this anymore. So my first job is to look at this program and try to make sure that it is reset. Okay, it is reset correctly. And the program counter is at location 00, so everything is good to go. The only thing I need to do is to change the register bank so that register B and register D will have some interesting value to trigger the overflow flag to become a 1. So I'll let you guys think a little bit about a subtraction and how can we make the overflow flag a 1. How much do you remember from the binary subtraction module? Okay, what does it mean when we have an overflow in a subtraction? The sign, yes, go ahead. 00 minus AA will never trigger the, well, okay, 00 minus 80 would trigger the overflow flag, but minus AA will not trigger the overflow flag. So the only way to trigger the overflow flag is for the result of a subtraction, the sign of the result of a subtraction not to make sense. In other words, we are out of range. Okay, you look at a subtraction, and the result of the subtraction has to be out of range. So that means you are probably looking at the most negative value, okay, as B, or you're looking at the most positive value for B, and then you want D to be some kind of negative value. Okay, so there are several ways to trip the overflow flag. So okay, I'll just give you an example. Okay, I'll just give you an example. We're gonna make B to represent the most negative value, which is 80 in hexadecimal, and then we are just gonna subtract 1 from it. So that means what this is doing is we are subtracting 1 from negative 128, which makes it negative 129. But negative 129 cannot be represented in a 8-bit signed integer. So that's why it's going to trip the overflow flag along with some other flags. Okay, but we are only focusing on the overflow flag. Are we good so far? All right. So I'm reusing things that we have talked about in the past, which has to do with the overflow flag and why, under what condition is it going to become a 1. So now we go back to main and we are ready to go. Okay, so we're going to go through the usual stuff, okay, which is fetch, increment microcode pointer, increment program counter, and then decode. So now we are ready to execute the compare instruction. So now we look at all the active components and see which one is in effect. So you can see that RI mux is a 1, but input enable is actually a 0. So that means none of the register is getting changed, which is consistent with the RTL that we are not storing the result back into any register. We can also see the ALU is active because ALU's own enable is a 1. Okay, this y over here, that's a 1. So that means we're performing some kind of calculation. If it's performing some kind of calculation, we want to find out what it is going to do. So we go into the ALU, and then we say, okay, these multiplexers and these demultiplexers and this multiplexer are all active because of this. Okay, they're all enabled. So if they're all enabled, we want to know, which of these calculations is actually being active. So that is specified by opcell, which is 001 at this point, which means output 1, in and input 1, these are active. So that means everything points to the subtractor here. So we are performing some kind of a subtraction operation because that particular component is getting the input from the input pin in 1 and also the input pin in 2. And then whatever is the output, it's going somewhere, but we are actually tossing the result. So now we want to find out who is giving the content, into the first wire, the top one into the subtractor, and who is supplying the value to the bottom one, which is here. So that means we have to go back out, and then we look up the first in one is coming out of this demultiplexer. The demultiplexer is enabled, and the select is 0, 1. So that means the input here is in fact connecting to the output, which is connecting to in 1. But this output is coming out of out 0 of the register bank. So that means we have to look into the register bank and then we ask, okay, who is supplying the value to here? So because this is the output of the multiplexer has a select of 0, 1. So that means input 1 of the multiplexer connects to the output. So now we track down input 1 and who is connected to it? Oh, guess what? Register B is connected to it. Are we good so far? Yes, I did talk very fast because this is something that we have talked about already. Okay. So now we can do about the same thing, and I'm not going to do it anyway because we will figure out, we'll find that into ultimately connects to out 1, and out 1 itself connects to the output of register D. So that means when we look into the ALU, we can confirm that this is coming from register B, this is coming from register D. Are we good so far? So that means we're performing the subtraction using the value of register B as X. We're using the value of register D as Y. And then the output is simply X minus Y or B minus D. Okay, we take a look at this. Seems to make sense because 1, 0, 0. Okay, 1, 0, 0, 0, 0, 0. Take it back. 0, 1, 1, 1, 1, 1, 1, 1, 1, 0 followed by 7 ones. Um, No, take it back. Okay. That was my bad. 1 followed by 7 zeros minus everything are zeros except for the least significant being a 1, having the output of 0, 1, 1, 1, 1, 1, 1, 1 is correct. Okay. So we already know that this output is not going anywhere because nothing in the register bank is getting updated. So now the question is, so what is the whole point? So the whole point is there's another register that is getting updated. See this green wire here, the light green wire? It is going into the flags register. So the flags register is getting updated. So that means you have to ask the question of who is supplying the value to update the flags register. So you follow this wire. That wire comes out of the flags out port of the ALU. So now we go back into the ALU and then we try to track down, okay, what the heck is that? This is flags out. So flags out is the output of this particular merger, which is also known as a splitter, but in reverse direction. So now the question is, what are those bits? What is C out, Z out, S out, O out, and so on? Well, this is, I remember as a kid, I used to, do a lot of puzzles, where, they would tell you, this is a clue, go here, and then track down everything. I did that a lot. So that's basically what you need to do to understand the ALU is to track down those tunnels. Okay, so we'll work with the first one first. What is C out? So C out is coming out of here. It is coming from a multiplexer. The multiplexer is enabled, and then the select is 0, 0, 1. So that means it is coming from a tunnel called B in this particular circuit. And then you look up, okay, where is B? B is right here. So B is actually the overall borrow of the subtractor. We good so far? So in our terminology, when we talk about binary addition and subtraction, that is equivalent to our T8. Okay, it's bit 8 of the T row. Okay, so now let's move on to the next one, the Z out. Okay, this is Z out. Z out is a little bit different because we never really talked about it. It is right here. This is Z out. It is the output of a NOR gate. This is a NOR gate because it is a OR followed by a negation. The bubble means negation, so it's a NOR gate. So you can also see how the output here, they're basically all ones except for 1, 0. But because we are ORing all of these zeros and ones together, so the output of the OR before the negation is a 1, but after the negation, it becomes a 0. And that's why the Z flag is a 0 in this case. All right. Then we move on to S out. S out is actually super easy. Okay, this is the easiest one to understand because you just have to look it up. It's like right here. Okay, this is S out. How do we get to S out? It is this is a splitter. that takes only bit 7 of whatever the output is and put it into S out. In other words, it is the sign of the difference in a binary subtraction, otherwise known as D7 in our terminology in binary subtraction. Okay, that's our sign flag. So the sign flag is super easy, okay, in this sense. So now we look at O out. Okay, O out is overflow. So you can see O out is coming out of here from this multiplexer. It is active. The select is 001. We track down input 1. And this is the circuit that actually does the computation of whether there's an overflow after a subtraction. Okay, S1, S2, and S out. Okay, we know where S out is coming from. S out is essentially our D7. So now we just need to figure out what is S1 and S2. So we track down S1 first. Okay, click on it. And then you just look at all the thick wires of S1. And we can now see that S1 is over here. It is bit 7 of X. In other words, S1 is the same thing as X7 in our terminology when we talked about binary subtraction. And then likewise, S2 over here is bit 7 of Y. So that's basically just Y7. So that means, oh, okay, so we have the most significant bit of X, we have the most significant bit of Y, and the most significant bit of the difference. This AND gate is negating the most significant bits of X and Y first, but then it does not negate the most significant bit of the difference. This AND gate, on the other hand, will take X7, Y7 not negated, but it does negate D7. So that is, and then both of these AND gates are feeding to an OR gate. So this is basically the same thing as the overflow expression that is in the binary subtraction module, except it is expressed as gate logic instead of a single expression. Are we doing okay so far? Okay. So in this case, do we have a overflow? And yes. Oh, okay. I explained everything wrong. I stand corrected because this is the one for the subtraction. This is for addition, which we're not doing. This is for the subtraction. Okay, that's my bad. I do apologize. So what I'll do is I am going to take a snapshot of this, and then we are going to go back to the notes just so that we can see how the gate logic corresponds to the expression. So now we switch back to the, oops, there we go. So we now switch back to the notes of binary subtraction. There we go. Not sure whether that's the right module. Nope, it's not. Let's see. I think I collapsed, that whole thing. That's why I couldn't find it. Let me go back to physical states. There we go. It's actually binary, not subtraction. It is comparison. So I have to go back one more time. Alrighty. Subtraction and compare. Binary comparison. That's the right one. There we go. All right. So it does talk about the overflow flag. And it is stated here. There we go. So this circuit here that we are seeing is implementing the expression here. Because S1 is the most significant bit of X, S2 is the most significant bit of Y, S out is the most significant bit of D. So this particular AND is the bottom one. This particular AND is the top one. And then this OR is this OR gate over here. Okay. So now we have a one-to-one comparison to basically go like, oh, okay. So for something that looks this complicated as an expression, in terms of being a logic gate or in terms of a circuit, it only looks like this. Not terribly difficult to grasp. All right, and it is a one. Okay, as expected, it is a one. So that's the overflow. And what about the last one here? What do you think that is? I didn't give it a name. Okay, it is the exclusive OR between the sign flag and the overflow flag. You can see how they're connected. So which flag is that? The L flag, exactly. Okay, that's how the L flag is computed. So that means when you look at flags out, the way we interpret these five, individual bits is this is our L flag, this is our overflow flag, this is our S flag, sign flag, this is our Z flag, and this is our carry or borrow after a addition or subtraction. Are we good so far? More or less? Mm-hmm. Hmm. It will only retain the last one. It will stay that way until it is overwritten by another add or subtract or compare. Yep. Okay, that's a good question. So the flags register is a register. So that means unless it is updated, unless the EN of the flag register is a bright green and then it gets a new content, otherwise it retains its the value of the individual flags. All right, so now we go back to main. Okay, we go like, oh, okay, so now we understand, why we are storing something into the flags register. So in fact, with this, clock here, we are about to have a rising edge. What we saw earlier, which is 1, 4 in hexadecimal, is going to be stored in the flags register. So Control T, oh, it's 1, 8. Sorry, it is not 1, 4, it is a 1, 8. So it is stored, okay? So that completes the compare operation, and we are now ready to move on to the next operation. So it's going to go from E70 to E71, which will turn it back to 000 for the next fetch phase. So we'll see that right there. So now we are ready to fetch the conditional branch instruction. So fetch, increment microcode pointer, increment the program counter, and decode. And now we are in the execute phase of the conditional branch instruction, the JOI instruction. So the JOI instruction, let's go back to the RTL description. There we go. So we are now looking at this particular RTL description. Okay, what is it saying? First of all, when you see the question mark and the colon in a C expression, what is the name of that type of expression? Is a ternary operator. Yes. Okay. So this is a ternary expression. And how do we interpret a ternary expression? What does the first part mean? What does it do? Go ahead. It's an if statement. So the first part is which part of the if statement? Is the condition of the if statement. Very good. So what is in between the question mark and the colon? The true value, right? It is the then portion. And then what is on the right hand side of the colon? Is the else. Very good. Okay, so in other words, this is a if then else in a single expression. It means let's take a look at the overflow flag. If it is non-zero, then we are going to return whatever the program counter is pointing to. Otherwise, we're just going to return the program counter plus 1. Okay, and this is the only mechanism of the entire processor that can quote unquote make a decision. This is the only way it can branch. There are two possible branches, and it has to take one of them, depending on, in this case, the value of the O flag. Yep. Hmm. So what you're talking about is true. The more branching or the especially conditional branches that you do, the slower the processor will go. Um, that has to do with breaking what we call a pipeline inside the processor. TTP is not a pipelined processor architecture, so it doesn't get affected by that much. On the other hand, with any modern, actual processor, they're pipelined, and what it happens is, with a pipeline, you are basically think of this, think of instruction execution like an assembly line. Okay, so instead of having the same person to put all the parts together and then hand it out, each person is only putting a part onto the final assembly. So now you have like four people. One person is going to put part one, and then the next person is going to put part two, part three, and then part four, right? And then the output would have all the parts A, B, C, D, right? But these four people can work in parallel, and therefore making the whole assembly process faster than a single person putting parts A, B, C, D all together, in four different steps. The problem is when a particular part is halfway assembled, somebody goes like, wait, this is not what we want. Then you have to restart the whole thing. So that's called breaking a pipeline. And conditional branches, you know, do that because you cannot determine which way the program is going to go until the flags are available. But because the flag is only available after the previous instruction is fully executed, so that means you probably will break the pipeline because you cannot predict which way to go. Yeah, they have advanced architectures that can go like in both directions. It's like, okay, I don't care which way we're gonna branch because I'm predicting both branches, and then once it knows the answer to the question, it will abort one half of the pipe and then continue with the one side that actually is what happened. So yeah, but that takes a lot of silicon. Okay. Yeah, this is what you will learn at UC Berkeley, probably a little bit, in their final class in the EECS, degree. All right, excellent question. All right, so let's go back to the processor. Okay, we have now decoded the conditional branch instruction, and we want to find out how it gets the job done. So you look at this and you go like, Tech, this doesn't look any different from the JMPI instruction. Okay, the RAM is selected, we are reading it. The D part goes to this multiplexer, it is selecting one, so this it goes here. This is also a one, it is going to the program counter. So the program counter in return is also going through this multiplexer to go to the A port. So it looks identical to the JMPI instruction at this point. But that's only because the overflow flag is a 1. So the key to understand conditional branch as opposed to unconditional branch is right here. Okay, let me point to the PC mux here. So the PC mux is not something coming straight out of the ROM. Okay, you cannot find a single wire in the ROM coming out of the ROM to contribute to PC mux. Instead, the PC mux as a tunnel is the output of this multiplexer here. So now you go like, oh, okay, so how does this multiplexer choose the input to become this output? So when you look at PC mux, because it is a multiplexer feeding to a multiplexer, it is a 0, 1, 1 at this point. So now what does that mean? When the select of a multiplexer is 0, 1, 1, which input is it choosing to become the output? Input 3. That's right. So you go like, okay, this is input 0, this is input 1, this is input 2, this is input 3. Input 3 is coming out of a splitter. That splitter goes into a wire. That wire in return goes to the output of the flags register. So we are really looking at bit 3 of the flags register. And what do you think is the value of bit 3 of the flags register? The flags register has a hexadecimal representation of 1 8. The 1 is 0 0 0 1. The 8 is 1 0 0 0. This is bit 0. This is bit 1, bit 2. This is our bit 3. That's why it is a 1. Is that okay? So that means when the flag of the conditional branch instruction, in this case the overflow flag, is a 1, the conditional branch instruction acts as if it is just a regular JMPI instruction. So you go like, so then what if the flag is a 0? What is it going to do? Okay, now we can kind of analyze that first, okay, and then I'll show you what it actually would do. So basically, we are hypothetically speaking, what if this wire is a 0? That means this wire is going to be a 0, which also means this wire is also going to be a 0, which means for this multiplexer, it is going to choose input 0 instead of input 1 to present to the output. So that means we're just incrementing, because that is the wire that connects to the adder that is simply adding 1 to whatever the program counter has. That is the mechanism of making a decision, which is also documented here, because if the overflow flag is a 0, then we are just going to add 1 to the program counter to update the program counter itself. Otherwise, if the overflow flag is a 1, then we basically do the same thing as a JMPI instruction, which is going to the location where the program counter is pointing to, grab the content of that location, and then use that to update the program counter. So this is really the core of decision making in the processor. And you might say, but Tech, yours is a toy processor. Obviously, it is a little bit simple. Nope, this is actually how all processors work. At the very core of every single processor, this is how it makes the decision. Yes. Nope. Nope. The only decision is, do you want me to go to where you specify or just kind of fall through to the next instruction? Those are the only two choices. So we have to make up the illusion of an else branch using some other means. Yep. So we'll talk about that in a separate lecture, probably sometime next week, because what you're asking is how do we use these really primitive instructions to implement more complex concepts in C++ programming. So that's compiling. So we'll talk about that too, but not today. Yep. All right. So I think that is the conditional branch instruction. So I got that done too. And this is the agenda. Okay, so we are done with a conditional branch. Now we want to move on to the increment instruction. I'm just looking at the time to make sure that I got everything covered. The recorder is still on. It is recording everything, including the voice. So we're good. Okay, we are on time right now. So let's take a look at the increment instruction. We go back to the opcode table, and then we look at the increment instruction, which I think is down there somewhere, right here. Okay, so this is the instruction opcode. So the first thing you notice is that looks a little odd, okay, because normally we have XX and then YY or just XX in it. This one has got XX and XX. What's up with this? The second thing you might also notice is, wait, hold on a second here. These two are going to overlap. In other words, if I specify OR, let's say A and A, it's going to have the same exact opcode as increment A. So what is the processor actually going to do in that case? Because they boil down to exactly the same opcode. Okay, does everybody understand, the question that I'm asking? Okay, I can show you using the assembler. Okay, it is actually the easier way to do it. So let's go back to the source and then we change this program. If you want to take a snapshot, now is a good time. Okay, if you want to take a snapshot and you have not done so, let me know and I will just wait a little bit. Are we good? Okay, I can see people are still popping in right now. Are we good? Are we ready to move on? Yes? Okay. All right. So let me erase this entire program. So what I want to do, okay, AA is not really that impressive. Let's do BB, okay, because at least B is a 0, 1, so it's a 0 and 0, 1. And then we also want to compare this to increment B as two different instructions. They're both legit, okay? They're both syntactically correct. The problem is they assemble to exactly the same opcode. So that means to the processor, now it has a quote unquote a problem because when we decode the opcode of D5, is the ROM going to output the bit pattern to perform OR BB, or is it going to perform the increment B? The answer to that question is it's only going to do increment B. In other words, increment B, okay, in terms of the opcode table, increment B is hijacking certain patterns of OR XX because we don't need it, okay? Why would you want to do a bitwise OR of a register with itself and then store the result back into the same register? Because a bitwise OR of a bit pattern with itself is going to be exactly the same because 1 or 1 is a 1, 0 or 0 is a 0. So that means OR a register with itself does not make any sense. Okay, so that means so that means if x and y are the same, that opcode really is not useful anymore. So I'm basically quote unquote hijacking those specific opcodes to mean something else, which is incrementing x. Are we good so far? So increment x is hijacking opcode from or xy. And then you go like, okay, so does that mean and xy is also going to be hijacked? The answer is no. As it turns out, I lied a little bit earlier. Okay, there is a use of doing a bitwise operation of a register with itself. So and BB, for instance, or and CC actually serves one purpose. That one purpose has to do with the ALU. So when we look into the ALU, okay, you can see that the AND operation and also the OR operation, they both will go through the multiplexer and then they all both go out to here. But you can also see that no matter what the operation is, whether it's AND or add, subtract, and whatnot, they're going to change the sign out, this flag here, and also the Z out flag here. So that means AND AA or AND BB, those opcodes are actually useful to see whether a register is 0 or negative. It's a very nifty trick to get it done without actually using a compare instruction. So that's why I'm only hijacking OR, but not hijacking AND. AND is not hijacked. AND BB does exactly what AND BB is supposed to do. All right. So another question, okay, another related question here is, well, can't we just load a 1 into register, load, and then use add to do the same thing as increment? The answer is yes, but there's a minor difference. Um, increment X does not change the flags register, and that's intentional. I actually have to implement additional circuitry to make sure that increment X does not change the flags register because sometimes you want to perform increment register in certain context, but you don't really want to change the flags register. So that's why increment X and also decrement X, they do not change the flags register. You can increment from FF to 00. It doesn't trip the carry flag. All right, so that is the hijacking of the increment instruction. I'm just looking through all the topics and make sure that I'm hitting everything. Oh, logging. Okay, this is the last one. So one of the questions, it is actually worth, I think, 4 points or so. It's going to ask you to figure out how many times we execute a particular instruction. So to illustrate that, I'm going to give you a more complicated program. So I'll start with a node up here, and then we'll just go like LDI C with a particular value, let's say 5, and then we have a L1 here, and then we'll do a and CC to see whether it is 0 or not. If it is 0, okay, we go to a label L2, which is going to end the execution of the program. And if not, I'm going to put a 4 into register B, and then we will have another loop here, L3 and BB. If it is 0, JZI to L4 to continue a loop. So now we have a whole bunch of dangling undefined labels. I will fix that later. You don't have to fully understand what this program does, okay? Because all I'm trying to do is to make a program kind of complicated to illustrate the one point that I need to make. So don't worry too much about this program. So JZI to L4, and in this case, I'm going to decrement B, and then we do a JMPI back to L3, which is the beginning of the loop. And then over here, we have L4, and then over here, we have decrement register C, and then JMPI back to L1. And now we should only have L2 unresolved. I'm just waiting for the error messages to pop up. I'll just put it in here. Halt. There we go. This is the problem of using a spreadsheet as an assembler. You know, sometimes it's really slow. There we go. Okay, so we don't have any errors. Excellent. So go to RAM file, go to file, and then we download the CSV because I'm not going to key in this program by hand. Okay, that's a little bit too much to key in by hand. So we'll just go like, we call this loopy. Okay. And then we switch back to the Logisim. And this time I can do a Control R, reset everything. And then we go to the RAM component, go to load image, and then we go to the temp folder, get loopy into the program. All right. So I got everything almost set up. The only thing I still have not explained yet is I want to count the number of times I get to a particular instruction. So which one do you want me to count? Of all of these instructions, which one do you want to count as in how many times we got to that location? Pick one. Do you want to pick the JZI instruction here? Okay, let's do that. So I'm going to say count the number of times this instruction executes. Okay, I'm just self-documenting here just so that when you watch the video or when you take a screenshot of this, you already know what the program is about. Okay, so the first thing we need to do is to go to the assemble view and find out where that instruction is. So this is on line 10, which also means in the assemble code, it is on the same or similar row number after JZI. Oh, this is the JZI instructions, row 9. Sorry, I take it back. So this is row 9. What is the address of this instruction? So I'm testing whether you remember between column W, X, and Y, which one is the address of the instruction? Is column W. Yes. So in this case, it is 09. Okay. So in other words, I am trying to track how many times I fetch the opcode at location 09 because that will tell me how many times that instruction executes, right? So now we go like, okay, how can we do that? Well, you can do it manually, okay, which means you keep an eye on the program counter, you keep an eye on whether the instruction register is enabled, and you count the number of times that the program counter is 09 and at the same time the instruction register is enabled. You can do that manually. But that's going to take a lot of control T's, okay, because this program is going to go, it's going to go for a while. So let me just go ahead and start the ticking so you can see how long this program is going to take. Because we have double loop here, there's an inner loop, there's an outer loop, so it's going to take a while. Okay, that's completing one outer loop. We are still stuck in the inner loop, still stuck in the inner loop. Now go back to the outer loop, and so on and so forth. So if you're using Control T and use the manual method of comparing the program counter to location 09 and looking for the instruction register being a 1, well, that's going to take a while. Can you do it? Yes. Can you do it in time to turn in the lab? Probably not. So that means, maybe this may not be the best way to do it. So Control K, stop the whole thing, and we want to reset the whole thing. So that means I need the clock to be low and I then click the reset button here instead of the control R. So this will only reset, the state of the program, the processor, but without deleting the program. Okay, so what are we going to do? Well, as it turns out, under Simulate, there is a tab called Logging. So logging is going to pop up a window that I need to move into the monitor, into the projector like this, okay? So this is the window for logging. So first of all, you can select what you're logging. So there's a whole bunch of stuff that you can log. So what do you think is important to log in this case? What did I say in when I was just illustrating how to do it manually? Yes, op fetch is one, and what is the other thing that you might want to log? What do you what component of the processor do you use to compare to 09, which is the location of the instruction that we want to track? The program counter. Very good. Okay. So that means, okay, maybe we want the program counter itself, okay, add, and also op fetch. Okay, so the 2 here means it is in base 2, which is probably not what you want to do because you want to see 09, which is in hexadecimal. So you can use change radix to change the base. So you want to change that to base 16. If I were you, I want to change it to base 16. Obviously, you can use any base you want. Okay, so now we have set up that we want to log these 2 things with only one thing that I still need to explain. What exactly is op fetch? So op fetch is a op fetch is right here. So this is op fetch as an output pin. It is the end between the clock and also the enable to the instruction register. So that means op fetch is only going to be a 1 after a rising edge and only when the instruction register is enabled. So that means every time op fetch is a 1, that means we just completed a fetch operation, which also means right at that point, whatever the program counter is where we fetched the opcode. Okay, so that's why it is useful. So now the next question is, so can we log it to a file or should we log it to a table? So you have 2 options here. If you log it to the table, it means you're gonna have to read the whole thing and do all the counting by yourself, which can be done, okay, but it is not the most efficient way of doing it. If you log it to a file, then you can use Notepad or some fancy editor that you have in order to do some search. So I would do it to a file. So if you want to do it to a file, you just have to select the location. I'm just going to say loop.log, okay, click save, and then we can close the window now, okay. And what we can do now is to turn up the clock speed. I would advise you to do the same thing. Turn the click tick frequency all the way to the highest. So this way it's not going to go slow. It will go as fast as it can. And then keep an eye on the halt flag here. The halt output pin is going to turn into a 1 when the program is all done. Okay, so this way you know when you can stop. So Control K, like so, is all done. Control K again. So now we can take a look at the file. Now, I am a command line kind of person, so I'm just using command line tools to do this. You obviously can do something different. So I'm going to use my favorite editor, which is nvim, to take a look at loop.log, which is essentially a text file. So what I'm looking for is 09 for the first column, which is the program counter, and a 1 for the second column, which is op fetch. So we go like, oh, look at this. Okay, here's 1. And now I need to find all instances like that. Fortunately, in Vim, we can search for 09 and followed by a space or a tab and then a 1. So this way I can look at all the instances, but I will still have to add them up, which is kind of tedious, right? So if you use a Mac or Linux, you also have a program called grep. Grep is really useful because with grep, you can specify a pattern that you're looking for. In this case, it's a 09 followed by a space-ish character, and then followed by a 1. And then you just tell it, okay, I need to find this pattern from loop.log. okay? And it will give you all the, it will basically search and display all of those lines where we have that particular pattern. You go like, but tech, I still have to count all of these. This is tedious. I don't like tedious stuff. That's fine. Okay, you can pipe that to WC, which is word count. Okay, so word count will give you the line number. Okay, this is the number of lines from the standard input. So I can now say, okay, there are 25 of those. Cool, right? Except in your lab, you're going to have to do the experiment a few times by changing the conditional branch instruction. Okay, so that means you're going to have to run it again and again and again, and each time you have to reset the counter. So let's just say that I look at this program and go like, I want to change the program so that I don't put a, let me see, uh, okay, let me reset the processor first because this way it makes it easier to see. So turn the clock down and then go to reset. So I would say, okay, instead of a 5 here, I want to change this 5 to a 6. Okay, like so. And this time I want to count again. How many times am I going to go through that one single instruction? So you go like, okay, so sounds like you can just kind of do the control K again, right? So let's do that. Run the control K. Now it's all done. I go back to my command line and go like, okay, tech taught me this little trick here. 55. That's wrong because it's supposed to be 30. So it is 55 because unless you reset the file to start all over again, it is appending to the file. So that's why every time I rerun the program, it's only going to increase this count. It's not going to reset it. So to reset it, you have a few choices. You can either remove the file from the file system and force the logging mechanism to create a new file. That's one way to do it. The other way to do it is to do it inside the log interface. So let me go back to the log interface first. Okay, you go back to file. All you have to do is to reselect exactly the same file and then click save again. Because every time you re-specify exactly the same file, Logisim will actually detect that, hey, you have a choice now, okay? Do you mean to reset the whole file, which is overwrite, or do you mean to append the new output to the existing file? So in your case, in the lab, you want to choose overwrite. Are we good so far? So let me just demonstrate. So now I select overwrite, okay, and then I can close this window, make sure that I reset the whole thing back to location 00, which is also what you can do too. And I can now redo the whole thing, Control K until it's done. And now we switch back to, I use the command line, but you don't have to. And now it is reporting that I only got to that instruction 30 times, which is the correct answer. All right. So in your case, the number or the count is not going to be anywhere close to 30. Okay. It's going to be a fairly low number, but the actual number depends on your ID. So I cannot really tell you, even if I wanted to, what it is supposed to be, because it depends on your ID. So I think we just got everything done, okay, with 2 minutes to spare, which I guess is good for uploading the content. There we go. So I'm just going back to my little agenda here. Okay, yep, we got everything. Question. I guess so. I mean, depending on the editor, it might tell you how many times it was found. I am not sure. Are you using WordPad or Word? Oh, okay. Yeah, I'm not sure. Oh, did it? Oh, okay, cool. So that means I did not actually need to use a WC. All right, cool. Thank you for pointing that out. Okay. Are there any other questions about what we have talked about so far? If there are no questions, I will give you guys the access code of the lab and you guys can get started. Or take a break first. Alrighty. So we are going back to It's called Simple Branching and Code Analysis. It is now visible to you. Just refresh your browser first. And then the access code is JOY, of course. JOY, not JOI. JOY. There we go. And let me upload the lecture because you probably want to have it uploaded. Okay, let me get back to. Oh, let me stop the meeting.